So let's see here. Okay, so specifically, when we have the dipole-dipole interaction, so we'll say dipole, oops, I can't spell it all, but you already knew that. The dipole-dipole interaction with hydrogen and look at this, oxygen, nitrogen, and fluorine only. We call this the hydrogen bond. And it's important to note this is not an intramolecular hydrogen bond. This is an intermolecular hydrogen bond. Okay? So if we look at acetic acid, for example, acetic acid can make these beautiful dimers, two of them, right? That's all a dimer means. Two pairs, or one pair, I guess. A trimer, would be 3. A tetramer would be 4. So these types of molecules can make these lovely dimers because of the way they're both trigonal planar here in this carbon, this sp2 carbon. And they just line up so well. Like, look, it makes this lovely hexagonal shape, right? And so this dotted line right there, that's the hydrogen bond. And as it turns out, it's quite strong. It's incredibly strong. But it's also important to note, look, that this is hydrogen with only oxygen, nitrogen, or fluorine. So you can't make a hydrogen bond with hydrogen and carbon, or hydrogen and phosphorus. It's really only observed in oxygen, nitrogen, fluorine only. So this is all over the biological world. The hydrogen bond is incredibly important in biology. In fact, the hydrogen bond is the glue that keeps DNA strands together in the double helix pattern, right? So for example, if we look at some of these DNA residues, okay, adenine, thymine, guanine, or cytosine, right, A, T, G, or C, they are zipped up. I mean, you can take an RNA strand, which is one single DNA, right, one single strand, and another RNA strand, and they can just zip together like a zipper with the hydrogen bond. So for example, if we look here at adenine here, there's this amine group, this NH2 group, right? So that contains a hydrogen, and it can do a hydrogen bond with a neighboring thiamine with that hydrogen interacting with the oxygen. And so this becomes really strong now because they can also do another hydrogen bond on the other side of the molecule, where now this amine group, this NH group, here is interacting with this other nitrogen right here. So there's a hydrogen bond between hydrogen and oxygen and between hydrogen and nitrogen. If you look at guanine and cytosine, there's actually 3 hydrogen bonds between G and C that can get created. And again, it's important to note, this is not an intramolecular bond. This is not like covalent. They're not sharing electrons. It's just the mutual attraction of oppositely charged things. Hydrogen is slightly positive. So hydrogen, we'll say, is slightly positive, and oxygen, nitrogen, and fluorine are slightly negative. When they get close to each other, opposites attract. It keeps DNA glued together. So there's also some amazing examples of hydrogen bonding in water that I'll describe as we get to the end of this section. Okay. Oh, never mind. It's right here. Okay. So I'll talk about the hydrogen bond in water right now, but then I'll talk about some of these amazing properties at the very end. Okay. So as it turns out, hydrogen bonding in water is amazing. It's what gives snowflakes or ice crystals their unique, what we call dendritic structure. So in ice, these hydrogen bonds, right, they're lining up from hydrogen to oxygen, hydrogen to oxygen. And look, it makes this lovely hexagonal pattern. And so when you multiply that by a mole, right, imagine now a mole of these patterns. This is what gives you that really cool looking snowflake pattern, that snowflake crystal. And of course, no one snowflake is the same as another snowflake because occasionally this network gets disrupted, right? It's not a perfect hexagon all the way through, right? Occasionally there are other ions that get embedded into that water crystal structure or other organic molecules that get frozen with the water, right? And what becomes interesting when you melt these things, so water as a liquid, you know, it's constantly tumbling around like other liquids do, as I demonstrated right here, right? So these hydrogen bonds are constantly breaking and reforming as water molecules want to move around in this liquid phase. And as it turns out, that's strong enough that when I slosh it around, look at how the water can like rise up, right? It rises with itself. So when you slosh a liquid around, those molecules are dragging other molecules with them to the point where the whole damn thing acts like one continuous fluid. In fact, that's why we call it a fluid, right? Because it can adopt the shape of its container. Okay.